All right, we are going to go over critical points and extrema. Extrema is just a collection of minima and maxima, so a minimum value or point and a maximum value of point. The collection of those are called extrema. So first, in order to find minimum and maximum values and points, we need to be able to identify what a critical point is first. And so critical points occur when your derivative, so f prime of x, there we go, equals 0, or your f prime of x, your derivative, does not exist. So those would be the two cases in which you would have a critical point. Okay. The x value is the critical number and represents the x coordinate of the critical point. And to find the y coordinate of the critical point, we have to plug the x coordinate back into your f of x, your original function. So if they ask you for just the critical number, you're finding just the x value. If they want the whole point, you have to plug that x value back into your original function to find the y coordinate as well. So in this first example, for finding the critical points of f of x, we first find f prime of x, which would be 4x plus 4. And then we're figuring out where this equals 0 or does not exist. Now, this is a linear function, so it exists everywhere, but it will equal 0 somewhere. And that place happens to be at -1. And so this would be your critical number. But it wants us to find the critical points. So we actually have to find our y value. So you plug your x value back into your original function. 2 times -1 squared plus 4 times -1 and minus 3. 2 minus 4 minus 3 would give me -5. So your actual critical point would be the point -1 comma -5. That would be the critical point itself. So be careful as to which one it's asking you for. And then what we do with critical points is the first thing that we can do with them is we can determine whether or not critical points represent a minima or a minimum or a maximum. Maxima and minima is plural of that. So the first thing you do is you find your critical numbers. And then once you have those critical numbers, you have to make a sign chart with them. So that would be where you put your sign chart and then your critical numbers go here, right, as the certain x values. And then what we do is we apply the first derivative test, and this test is very well known in calculus. There is a second derivative test, but we'll get to that in a little while. So we're going to apply the first derivative test. So the first derivative test tells us that if your first derivative changes from positive to negative, so around some critical number, so let's say it was positive before this value and then negative after this value, our original function would have a local or relative maximum. And that makes sense because if I had on my original graph, so if I had a graph that had a maximum point, the slope before you reach that critical point, right? Critical point is where your derivative, aka the slope of your tangent line, equals 0. Before that maximum, you would have a positive slope, and then after that maximum, you would have a negative slope. So it would make sense that on a sign chart, before your critical number, you'd have a positive slope, and then afterwards, you'd have a negative slope. That would result in a local maximum. If you have a local minimum, it's because your derivative changes from negative to positive for the very opposite reason, right? So if I have some minimum value on my original function, you had a critical number there. Before you reach that, the slope of your tangent line is negative, and afterwards the slope would be positive. So that means you would be going from like negative to positive on your sign chart. And last but not least, if your derivative does not change signs, the function f of x has what we call a saddle point. And a saddle point looks either like, I'll draw both ways that it can happen. So you could have like that, oops, or this. And that would mean that you have your critical, oh, it's not the perfect drawing, but pretend that it's perfectly flat. Critical numbers would occur there and there. And then beforehand on this graph, your slope would be positive, and then it would stay positive. Oops. Stay positive afterwards, or it could be negative and then stay negative afterwards. So this isn't a minimum or a maximum value, it's a saddle point. We often, in my calc class, draw what we call saddle point dinosaurs to help us remember what it looks like. So however you need to remember it is fine. Oops. Go. Not the best dinosaur, that's okay. But look, he's wearing a saddle. He's happy. So there you go. There's your saddle point dinosaur. It has that kind of shape to it. And then the last part you have to do is if you found these values, right, you found where it changed, it was either a maximum or minimum or saddle point, the x coordinate or x value is where the min or max occurs. And then if you find your y value, so find the y value using your original function, so f of x. Oops. So your x value is where the min or max occurs. They find the y value using your f of x function, and that is the actual max or min value. Sorry, so number 4 is kind of a hodgepodge of information, but so once you find that x value, that's where it occurs, but then you find the y value using your original function, that would be your actual maximum or minimum value of that function. So we're going to try some practice here. So we're going to find the maximum and minimum points for this function. So the first thing, our first step is to find our critical numbers, and to do that we have to find the derivative, which would be 6x squared plus 6x. We have to set that derivative equal to 0 to find our critical numbers. So I can pull out a 6x as a GCF, and you have x plus 1 left over. And so then the x values that would be my critical numbers would be 0 and -1. So I'm going to slap those on a sign chart. -1, 0. And then now I'm applying your first derivative test, which means that I'm testing values in between these numbers on my first derivative, or in my first derivative. So I'll find f prime of -2, I'll find f prime of -0.5, and then I'll find f prime of 1. And for these, remember, we don't actually care about the values, you just care about whether it's positive or negative. And so I usually test them in my factored form of the derivative because it makes it easiest to see whether you have positive or negative answers just from multiplying. So like if you plug in a -2 in for your x values here, -2 times 6 is a negative number. -2 plus 1 is another negative number, so you have a negative times a negative, which is a positive. When we try -0.5, -0.5 times 6 is a negative number. -0.5 plus 1 is a positive number. So when you do a negative times a positive, you end up with a negative. And then f prime of 1, if I plug 1 in here, I get a positive number. And if I plug 1 in here, I get another positive number. And a positive times a positive is a positive. Okay, so now we can confirm some things about these critical numbers. So we would say that at x equals -1, we have a local or relative max. And then your justification for that would be because f prime of x equals 0 and changes from positive to negative. At x equals 0, we have a local min because f prime of x equals 0 and changes from negative to positive. And then we actually have to find the points still, so I can plug these values back into my original function to find the actual points themselves. So if I find, just off to the side, f of -1 and then f of 0, f of 0 is easy. F of 0 is just -4. This one, let's see, so you get -2 plus 3 minus 4, so you get the point -1 comma -3. So -1 is where your max occurs, and -3 is the maximum value. And then for the second, or my local min, 0 is where the minimum occurs, and then -4 is my minimum value. And so then those would be the actual points themselves. This part right here is 100% required anytime you need to provide justification. This is needed, especially on FRQs, or only on FRQs. You don't have to show anything for multiple choice. But on FRQs, it has been deemed by the AP Calculus community that a sign chart alone is not enough. You need the actual wording justification. So make sure that you write that down. One more thing that I forgot to clarify earlier, when we talk about relative or local maxima and minima, I just want to talk about what that means. So when I talk about local or relative maxima or minima, this means, and this is mathematical terminology, that means in a particular neighborhood that you have a maximum or a minimum point. So I don't want you to think that these are, when we're finding these answers, that they're the very maximum of the graph or the very minimum of a graph, because you could have a graph that has like multiple different maxes and mins. So these would be all local or relative maxes, and then these would be all local or relative minimums, because in that particular neighborhood, that's the highest point. So maybe go back and write that note down specifically. And then I just wanted to look at a last example where we're not given a function itself, we're given a graph instead. So the graph of the derivative of function f is shown below. So this is the graph of f prime. We want to know, or the graph is horizontal tangent lines at -1, 1, and 3, and they want to know at what values of x does your original function have a relative maximum. Now I don't have any information about my original function whatsoever, so it would be helpful to identify like what this would mean in terms of the derivative, because I have derivative information. So if f has a relative maximum, that means my derivative either equals 0 or does not exist, and changes from, if it's a maximum, positive to negative. So looking on this graph, there are 3 places where my derivative equals 0. Right here, and right here. There are no places where it doesn't exist, so I don't have to worry about that. And now we just have to look and see, where does my derivative, aka this graph, change from the positive to the negative. So positive means the positive section to the negative section. So where does your graph change from positive to negative? And that happens at 4. My graph changes from positive to negative. So we would say that x equals 4 is a local or relative max. And then your reasoning would be the because this statement up here. Whoops. Because f prime of x equals 0 and changes from positive to negative. So there you have a local max here. And then just to talk about it a little bit more, at -2, your graph goes from negative to positive. So this would be a local min. And then at 1, your first derivative graph equals 0, but it doesn't change sign. So on our original graph, we would have a saddle point. All of these things, the local min, the saddle point, and the local max, would be occurring on your original function. We're just identifying from our derivative graph what's happening there. So there we go.